Now we move to another saccharide, that is sucrose. Sucrose is also called as our table sugar, or it is also called as cane sugar, and the molecular formula of sucrose is C12H22O11. And we know sucrose is a disaccharide. Why it is a disaccharide? Because sucrose on hydrolysis will give you two monosaccharides. So sucrose is an example for a disaccharide. Sucrose on hydrolysis will give you glucose and fructose. Glucose and fructose are monosaccharides. So sucrose is an example for a disaccharide with a molecular formula of C12H22O11. See, sucrose will give you glucose and fructose. The molecular formula of glucose is C6H12O6, while the molecular formula of fructose is C6H12O6. So when we add the molecular formula of glucose and fructose, we should get C12H24O12. But we are getting C12H22O11. That means when glucose and fructose combine to form sucrose molecule, one water molecule is eliminated, or there is a difference of H2O. And we know we get sucrose from our cane sugar. So industrially we are taking cane sugar and we are powdering it, and it is crushed into juice. So the juice is then heated until the water evaporates and syrup forms. So we will crush the sugar cane and we get the juice out, and the juice is then heated until the water evaporates from the juice out, and we will get a thick syrup form. This syrup is then boiled so that raw crystals of sugar will be crystallized. So as the concentration increases, raw sugar crystals will crystallize out. And this is not a pure form of cane sugar. This is the raw form of cane sugar. This raw form of cane sugar we take and again liquefy into a type of liquor. So that raw sugar we will again make into a liquid form, a concentrated liquid form. Then the liquor is processed through a stage called carbonation, so that it will remove the other byproducts. Along with the cane sugar, other solid byproducts are there that will be removed by this carbonation process. The resulting liquor or syrupy solution is then decolorized to get white color. So the decolorization is usually carried out by animal charcoal or wood charcoal, so that the colors of the pigment of the cane sugar will be adsorbed and we will get white color of granulated sugar. And this is boiled so that sucrose crystals form again, and then dried with hot air to obtain final cane sugar molecule. So in industry, these are the process we do to obtain our table sugar or cane sugar from cane sugar plants. So they may ask, how will you prepare sugar or cane sugar industrially? This is the process. Take down. Now we have to see an important phenomenon called inversion of cane sugar or inversion of sucrose. As I told you, sucrose molecule on hydrolysis in presence of mineral acids will give you glucose and fructose. Glucose and fructose. So, sucrose molecule is a disaccharide. It on hydrolysis, that is treating with water, in presence of a mineral acid, gives glucose and fructose. If I take 1 molecule of sucrose, I will get 1 molecule of glucose and 1 molecule of fructose. That is why I told you equimolar amount of glucose and fructose. But it is observed that sucrose solution is dextrorotatory. Sucrose solution is dextrorotatory. That means sucrose solution will rotate the plane polarized light towards the right direction. So the specific rotation of sucrose molecule is towards the right direction. That means it rotates the plane polarized light towards right direction. And after hydrolysis, if I check the specific rotation of the resulting solution, that is mixture of glucose and fructose, it is observed that the resulting solution is levorotatory. That means the resulting solution rotates the plane polarized light towards the left direction. So, after the hydrolysis, the specific rotation is changing to the left direction. See here, sucrose is dextrorotatory with a specific rotation of plus 66.5. But after hydrolysis, the resulting solution becomes levorotatory. This hydrolysis of sucrose to an equimolar mixture of glucose and fructose is always accompanied by a change in optical rotation from dextrorotatory to levorotatory. This change in specific rotation of sucrose molecule during hydrolysis is called inversion of cane sugar. You got the point? So I have sucrose molecule which is dextrorotatory having a specific rotation of plus 66.6. Plus means dextrorotatory. The resulting solution become minus levorotatory. So the specific rotation is changing from sucrose molecule to the hydrolysis products glucose and fructose. This change in specific rotation is called inversion of cane sugar. Very, very important. Now we have to see what is the reason of inversion of cane sugar. Why the specific rotation is changing from dextrorotatory to levorotatory? The reason is very simple. I told you in case of sucrose molecule, the specific rotation is plus 66.5, and there is a positive sign. It indicates it is a dextrorotatory sugar. But after hydrolysis, I will get glucose having a specific rotation value of plus 52.7, while the same mixture contains fructose which is having a specific rotation value of minus 92.4 degree. That is a minus sign. This is a plus sign. So the resulting mixture contains equal amount of glucose and fructose. But for glucose it is positive 52.7. That is dextrorotatory. But for levorotatory fructose it is minus 92.4. So in that particular solution I have plus 52.7 and minus 92.4. So naturally the solution will be dominated as levorotatory. Why? Because the minus 92 and this is plus 52. So the resulting solution become levorotatory due to the presence of fructose molecule. So plus 66.5 is the optical rotation of sucrose. But when it gets converted to glucose and fructose, the fructose is dominating over glucose. This is the reason for the specific rotation. See here, 66.5 degree changes to 52.7 and minus 92. So this part becomes predominantly negative. That is why this resulting solution becomes levorotatory. Take down. Now we have to move for the structure of sucrose or structural elucidation of sucrose. We have elucidated the structure of glucose molecule and fructose molecule, and elucidation of structure of sucrose molecule is bit more easy. So we have to proceed for this one using different steps. So what is the first step? The molecular weight determination and elemental analysis confirms the molecular formula of sucrose is C12H22O11. By experimental studies, it has observed the molecular formula of glucose is C12H22O11. This is the first point for the structural elucidation of sucrose. So see second point. Sucrose on treating with acetic anhydride, that reaction is called acetylation. So it on treating with acetic anhydride, it gives you octa-acetate sucrose. What is the importance of acetylation reaction? Acetylation reaction will give you the idea about how many OH groups are present in a particular molecule. So sucrose gives you octa-acetyl derivative. That means octa means 8. This clearly confirms that sucrose molecule contains 8 OH groups. Since sucrose molecule is highly stable, these 8 OH groups should be present in different carbon atom. See, on acetylation I am getting octa-acetyl sucrose, and this octa-acetyl sucrose is highly stable. That clearly indicates that these 8 OH groups are present in different carbon atoms. So the second point is the acetylation reaction, which confirms the presence of 8 OH group in sucrose molecule. See the next one. Sucrose on hydrolysis with acids or enzymes gives equimolar solution of glucose and fructose. Equimolar solution means equal amount of glucose and fructose. This confirms that one molecule of sucrose is made up of one molecule of glucose and one molecule of fructose. See, when I take sucrose and I am carrying out hydrolysis, I get equal amount of glucose and fructose. Naturally, it means that one molecule of sucrose is made up of one molecule of glucose and one molecule of fructose. So we could say the disaccharide contains a glucose molecule and a fructose molecule. We know the structure of glucose molecule and we know the structure of fructose molecule. And we know the Pirano structure of glucose molecules and the Pirano structure of fructose molecule and the Furano's, F-U-R-A-N-O-S-E, Furano structure of fructose molecule. See here, sucrose does not reduce tolerance reagent. Sucrose does not have any reaction with the tolerance reagent. It does not show mutarotation. Sucrose does not show mutarotation. It neither reacts with phenylhydrazine nor reduce Fehling solution. All these reactions are indicators of carbonyl group. If a molecule contains carbonyl group, it reacts with the tolerance reagent, it shows mutant rotation, it shows reaction with the phenylhydrazine, and it reduces filling solution. But sucrose molecule does not give any of these reactions. This clearly indicates that sucrose molecule does not have a free carbonyl group. Sucrose molecule does not have a free carbonyl group. That means glucose is having free carbonyl group, that is the aldehyde group. Fructose is having a free aldehyde, free ketonic group. But when glucose and fructose is combining, the resulting molecule sucrose does not have a ketonic group or a aldehyde group. If there was ketonic group or aldehyde group, surely, naturally it should give reaction of tolerance reagents, mutant rotation, and Fehling solution and phenylhydrazine reaction. But it is not giving any of these reactions. This shows that when glucose and fructose combine to form sucrose molecule, the sucrose molecule does not have a free carbonyl group. Take down. Sucrose, on treating with dimethyl sulfide in an alkaline solution, gives a mixture of 2346 tetramethyl D-glucopyranose and 1346 tetramethyl D-fructofuranose. This clearly shows that sucrose molecule is made up of pyranose ring and furanose ring. We have studied that glucose could exist as a pyranose ring, while fructose could exist as pyranose ring as well as furanose ring. So, we have conducted dimethyl sulfide test in alkaline solution. So, we got 2, 3, 4, 6. 2, 3, 4, 6 glucopyranose and 1, 3, 4, 6 tetramethyl D-fructofuranose. See here, this is 2, 3, 4, 6 glucopyranose. First glucose combined with fifth glucose to form a pyranose ring structure. That is why second position, third position, fourth position and sixth position we have free OH group. So these four positions have free OH group. That is why it reacts with dimethyl sulfide. For fructose, we have first position, third position, fourth position and sixth position. That means second position and fifth positions are not here. So we could say this is a furanose ring. So we could confirm that sucrose is made up of a pyranose ring of glucose and a furanose ring of fructose. So this is a 6-membered pyranose ring and this is a 5-membered furanose ring. I hope you are remembering the glucopyranose structure. Please draw it in your book or turn your notebook and see the glucopyranose structure. The first carbon atom is connected with the fifth carbon atom and it is having a hexagonal structure. While for furanose, we have a pentagonal structure or pentane structure in which the second carbon atom is combined with the fifth carbon atom. So we confirmed the molecule is having pyranose and furanose ring. Now the question comes here is, glucose exists as two pyranose forms. Which are they? Is alpha D glucopyranose and beta D glucopyranose. Similarly, fructose exists as two forms. Which are they? Alpha D fructofuranose and beta D fructofuranose. Now we have confirmed that in sucrose molecule, glucose is in the pyranose form. So we have to confirm whether it is alpha pyranose or beta pyranose. And we have seen that fructose is in the furanose form. So now we have to confirm whether it is a alpha or beta furanose. Got the point? So we have confirmed sucrose is made up of pyranose of glucose and furanose of fructose. Pyranose of glucose is a 6-membered ring, while furanose of fructose is a 5-membered ring. So sucrose consists of 6-membered glucose molecule and 5-membered fructose molecule. Now we have to confirm whether it is alpha or beta form of glucose and fructose. See here, sucrose is hydrolyzed by maltase to form glucose and fructose. So the enzyme maltase undergoes hydrolysis for sucrose. Then maltase is an enzyme which only hydrolyzes alpha glucose ring. Alpha glucose rings are hydrolyzed by maltase. We know maltase is an enzyme. Enzymes are specific catalysts, very specific catalyst. So maltase is an enzyme which converts sucrose to glucose and fructose, and that is a specific enzyme which only hydrolyzes alpha glucose ring. Okay, that means in sucrose molecule the glucose is a alpha glucose. So in sucrose molecule we confirmed sucrose molecule is made up of alpha D glucopyranose. Now we have to move out fructose. See here, sucrose is hydrolyzed by an enzyme invertase. It is an enzyme invertase which only hydrolyzes beta fructofuranose. Only hydrolyze beta fructofuranose. So the enzyme invertase converts sucrose molecule to glucose and fructose. So it again confirmed that in sucrose molecule it is beta D fructofuranose. So we have confirmed sucrose molecule is made up of pyranose of glucose and furanose of fructose, and now we confirmed sucrose molecule is made up of alpha D glucopyranose and beta D fructofuranose. Now you draw the structure of alpha fructofuranose, beta fructofuranose and alpha glucopyranose. I repeat, alpha glucopyranose and beta fructofuranose. Draw the structure soon in your paper, in your book, in your notebook. I hope you have drawn the structure of alpha D glucopyranose and beta D fructofuranose. See here, this is alpha D glucopyranose. This is the anomeric carbon atom. OH is on down for alpha D glucopyranose. Now see here, This is beta D fructofuranose. See here, the OH group is above the plane. This is the anomeric carbon atom. Now, this OH of alpha D glucopyranose combine with the H of beta D fructofuranose. See, anomeric carbon atom is having carbon. This is the anomeric carbon atom. Anomeric carbon atom is having OH group. This OH group H and this anomeric carbon atom OH is eliminating. So, the valency of this carbon has lost. The valency of this oxygen has lost. So, they result in the formation of a molecule like this. See here, the anomeric carbon atom of alpha D glucopyranose connected with the anomeric carbon atom of beta fructofuranose. These are connected. So, we have seen anomeric carbon atom is the reason for mutarotation. But here, anomeric carbon atoms are connected between two. Hence, this cannot exhibit mutarotation. That means there is no free aldehydic or ketonic group in this particular molecule. So, we say alpha D glucopyranose connected with beta D fructofuranose through 1,2 linkage. That means first carbon atom of alpha glucopyranose with second carbon atom of beta D fructose. This is called the glycosidic linkage. So draw alpha D glucopyranose, then beta D glucopyranose, then show this structure. This is the structure of sucrose molecule. Very, very important. See here. See, I am representing in a reverse direction. So here I am numbering from here 2, 3, 4, 5 in the anti-clockwise direction for fructofuranose, and for glucopyranose in the clockwise direction 1, 2, 3, 4, 5, 6. Here in the reverse direction 1, 2, 3, 4, 5, 6. See here. So first carbon atom of glucopyranose combined with the second carbon atom of fructofuranose. This is happening here. See the structure here. Oxygen linkage. This yellow color is the oxygen linkage. So glycosidic linkage. See here, glycosidic linkage. So this is the structure of sucrose molecule formed from alpha D glucopyranose and beta fructofuranose. An important question for examination. Draw the structure of sucrose. You should be very careful. You should draw glucopyranose structure in the clockwise direction, fructofuranose in the anti-clockwise direction. It is easy. You number from 1, 2, 3, 4, 5, 6 here. So, first carbon atom of glucopyranose and second carbon atom of fructofuranose. This is a three-dimensional structure showing this is glucose molecule, this is fructose molecule, a 5-membered ring, and oxygen linkage connection. Connection is here. This is the connection, and this is the bulky group. So this is the connection.